Okay, good afternoon. So today we will mainly focus on the topic of the stopping time, and these are optional stopping theorem. So so recall from last session we talked about a martingale, right? And basically we have a filtration of sub-sigma algebras. So let's say you have these are starting from F0, F1, F2, and so on, right? So this is a filtration of sub-sigma algebras. Okay, so what does this filtration really mean? The F0 basically consists of all the events, right? All the events that you can put that you can measure in terms of its probability. You are able to apply your probability measure, okay, to the events inside this F0. Similarly, F1, right, is a sigma algebra. It consists of a collection of events that you can measure, okay, their probabilities. So you can see that these sigma algebras, right, this is increasing in size. That means if you treat the index as the time, right, over time, you are basically observing more information in the sense that you are able to put a probability measure, right, on more and more events as time goes by. Okay, so that's why we call this the information structure, right, of this whole process. Okay, so this is just an information structure. It doesn't mean if there's a stochastic process, right, you will only at each time you will only observe a certain realization of events, right, at each time. But if it follows this, if it's your stochastic process is adapted to this filtration, then whatever event you observe, right, will have to belong to the Fn, right, at time n. Okay. So now we want to define the notion of a stopping time. Okay. So let's call it tau. So this is we restrict it to be an integer value random variable. So taking values in 0, 1, 2, and so on. Here we will also add in a special symbol called infinity to indicate the special case where this stopping time is basically the stopping time is not the stop or the stop state is never reached. Okay, so this stopping time is typically is used to represent the first time when a certain criteria is met, right? So later on we will see some examples. So basically you define a criteria and then you observe your martingale, and when it meets that particular criteria, then we say that's the first time, right, that he has met that criteria. So then we call that the stopping time. Okay, and of course the infinity will then just mean that that criteria is never met, right, in this whole stochastic process. So this is just to make it more general, but usually most of the time we will actually consider stopping times that are finite almost surely. Okay, so this is a random variable, and the mean stopping time is just a interpretation in the typical case where we basically associate this tau, right, with like the first time where a certain criteria is met. But of course, it can be very general. It's just really just a random variable that the integer random variable, and it has to satisfy this criteria whereby the set. Okay, so let me write it out in full. So tau omega smaller than n. So this set has to belong to your sigma algebra at time n. Okay, and this is true for all n. Okay, for every value, integer value n, this set has to belong to your sigma algebra n, right? Which means that at each time n, okay, I'm able to determine, okay, whether the stopping time is reached or not. Okay, so if your stopping time is corresponds to the first time when a certain criteria is met, this is just basically saying, like, for this guy, at every time n, I'm able to determine, right, whether that particular criteria has been met or not. Okay, so then this is called stopping time. Okay. Right. So okay. So notice that this doesn't mean that the tau is measurable with respect to Fn. Okay. For tau to be measurable with respect to Fn, it has to be that tau smaller than all integers k, right? Has to belong to Fn. But here we only require that tau smaller than n belongs to this Fn. Okay. So since Fn is a sigma algebra, then of course we immediately get that this set, right, which is just the complement of this set. So this has to belong to Fn. So because it's a sigma algebra, and of course tau equals to n, right? This set is nothing but this minus tau smaller than n minus 1. Okay, so this one by definition belongs to Fn minus 1, but because this is a filtration, Fn minus 1 is inside Fn, so both of them belong to Fn. Okay, so and since this is a sigma algebra, this will belong to Fn as well. Okay. Okay, so that's right. Okay, so in the typical case, most of the time we will do at stopping times that are finite almost surely. So we probably want your particular criteria will be met. Then we will define a random variable x tau, right? So let's say you are given a sequence of random variables x0, x1, and so on. Okay, and we want to define a random variable x tau, right? Where this is basically taking the random variable at the stopping time tau. Okay, and so this is defined to be just right when tau equals to k on the event tau equals to k, then it's equals to xk. Okay. So we then say that right this x tau is the stop process, the stop, right? So it's basically we are taking the random variable at the stopping time, okay, x tau. Okay. Okay. So we hope that if my xk is right, my xk is a martingale. I hope that my x tau is going to be a martingale as well, or observe certain properties of the martingale, especially the expectation. Right, I want to see under what situation the expectation of x tau has to be equals to expectation of x0, right, which is the constant expectation for your martingale. But unfortunately, that's not always true. Okay, but what we can say is a simple result whereby now if I take a n, right, and take the minimum between n and tau is my stopping time. Okay, so this is defined to be the minimum of n and tau, right? So certainly this is always finite, right? Because my n is finite. This is finite almost surely. And you can check that from this definition, right? You can just plug this inside here, that n minimum of tau by itself, is holding this is a stopping time as well. Okay. So this is something easy to check. So our first result, okay, first theorem says that if my mm is a martingale, okay, so I give you a martingale, right? Then it turns out that m n minimum of tau, okay, so treating this as a stopping time, right? So n minimum of tau, this is a stopping time. So m of this guy, right, is following this definition over here, right, where your tau is replaced by n minimum of tau. Okay, so it turns out that this is also a martingale, right? So let's try to prove this result. Okay, so first of all, without loss of generality, we can assume the m0 equals to 0. Okay. So let's just set m0 equals to 0, because if it's not equal to 0, you can just minus m0, right, from all the terms inside your martingale, and you still have a martingale. Okay, so for simplicity, let's assume m0 equals to 0. Okay, now we can define an to be the this indicator function where tau is bigger or equals to n. So this is the same as saying that tau smaller than or equals to n minus 1, the complement of this, right? So remember, tau is an integer value random variable. Okay, so these two are the same. So we saw before, right? So by definition, tau smaller or equals to n minus 1. This is in fn minus 1, right? And the complement is in fn minus 1. So this guy is measurable with respect to fn minus 1. Okay. So what we have defined an, right? This sequence of random variables, an is measurable with respect to fn minus 1. So if you recall, this is something that we defined last week to be a so-called a predictable sequence. Okay? So and moreover, because this is an indicator function, right? So it takes on 0, the value 0 or 1, so it's definitely bounded, right? So then we can make use of our martingale transform theorem from last session, right? Where it says that doing the martingale transform with respect to a predictable sequence that is bounded, okay, it will give you back a martingale. Okay? So your martingale transform will also be a martingale. So that's so what is your martingale transform here? So AK, this is just AK of mk minus 1, right? So k from 1 to n. Okay. So your martingale transform theorem, right, tells you that this is by definition, this is a martingale. So let's expand this out and see what happens. So AK, right? AK is defined to be this guy over here. So we can just plug in the indicator. So this is what is tau bigger than k. Okay, and then we can split out into two sums. And then this guy will be, okay, to n minus 1. So here I'm just shifting the index by 1, right? Instead of writing nk minus 1, I write mk, right? And then shift the index by 1. So that's why it becomes k plus 1 over here, okay? And then the indices, right, are going from this 1 to n minus 1, because m0 we assume to be equals to 0. Okay, so now we can simplify this expression. So this guy minus this guy. So in the first n minus 1 terms, you write mk, and this minus this, right? So you get tau equals to k, right? Of mk, and then you have one last term. Okay, in the first sum, there's the last term, which is tau bigger than n. Okay. So this by definition, right, is basically I'm taking the m tau but restricted to tau smaller or equals to n minus 1, right? So this is nothing but m tau, and then I restrict it to tau smaller or equals to n minus 1, okay? And this part is still the same. Right, so now yeah, so now if you look at this guy, right? So if n is smaller than tau, right, you will get this case, right? You get If n is strictly bigger than tau, then you get this case, then you get m tau, right? So my definition, this is just m minimum of n and tau, right? Okay. So we have just proven, right, from the martingale transform theorem, this tells me that this is a martingale. And we have just proven that this martingale transform is nothing but m and minimum of n and tau. Okay? So that's why this guy is a martingale. Okay, any questions here? Right, so this being a martingale, so that means the expectation, right? The expectation of n minimum tau will be just the expectation of, let's say, the first term, right? M0. Okay? So this is always true. Okay. Okay, let's do some examples first to see how we can apply this. Okay, so now I have random variables, IID random variables SI, and these are binomial Bernoulli random variables, right? Taking value 1 or -1 with probability half each. Okay, and as usual, we will define my, so let's start with S0 to be 0 and Sn to be just the sum of the Si's, I from 1 to n. And we saw last week, right? We proved that this is a martingale, right? Okay, now let's define a stopping time. So the stopping time that we are defining is basically the first time n when this sum Sn is equals to A or Sn is equals to minus B. Okay. So my A and B are two positive integers. Right, so what is this? This, if you look at this sum over here, right? So each time you are either +1 or -1. So we can think of this as actually a random walk, right? So each time you are going up, you are either going up one step or you are going down one step, right? So if you plot the Sn over the index n, so starting from S0 equals to 0, so maybe with probability half it goes up by 1, right? In the first time step. In the second time step, maybe it goes up by 1 again, then maybe it goes down by 1 and so on, right? Okay. So this is one realization, right? One realization of the Sn. So you can think of this, right? Basically, it's a random walk. And what this tau is saying is, I'm interested to look at the first time. Okay. So let's set a threshold A here over here, and the threshold minus B over here, right? So tau is the first time when my random walk either hits the upper threshold A or it hits the lower threshold minus B. Okay, the first time that it does that. Right, so that's why this is also called a first hitting time. Okay, so in the textbook you can also see this term is called the first hitting time of your boundary. Right, and I guess it is quite easy to verify that this tau is indeed fits the definition of the stopping time, right? Fit this definition. Okay, so you can verify that. So this is a stopping time, and so from our previous result, right, from this theorem over here, we know that my Sn is a martingale. So the Sn minimum of tau, right, this is also a martingale. Okay. So from the theorem, we know the Sn minimum tau, right, this is a martingale. Okay. So since this is a martingale, that means my expectation of N minimum of with tau is nothing but the expectation of S0, right? Which is we define to be equal to 0. Okay. So now I'm interested to know what is the probability, how to compute, okay? Two things. First of all, what's the probability that at tau, at the time tau, I'm hitting the threshold A, right? So you can either hit A or minus B, right? So I want to know what's the probability that you is going to hit A instead of minus B. Okay, and of course, then the probability of hitting minus B is just the 1 minus the probability of hitting A. So that's one thing. And the other thing is I want to be able to get an estimate of what's the, or rather I want to compute what's the expected time it takes before it hits either one of the boundaries. Okay? So the expectation of tau. Okay, so right, so we observe that if my Sn, okay, this process, if it has not hit minus B yet, right? So I still I'm somewhere in between, right? I haven't hit the minus B. Then if I take a sequence of let's say in the next uh time steps, in fact A plus B time steps, right, is happens to be all ones. All the Si's are equals to one, right? So no matter where you are, you haven't hit the minus b yet, then if I take another sequence of a plus b ones, then this Sn, right, will definitely hit the upper boundary A, right? Okay. So let's let Ek to be this event, Ek to be the event whereby my Xi's are all equals to 1. Okay, for all I inside this interval k of a plus b to k plus 1 of a plus b. Okay. And you note that this, because all these intervals, right, these are disjoint intervals, and my Xi's are all independent. So each of these Ek events, right, these are all independent. Okay, these are independent events. So we can compute what's the probability that my tau is bigger than n times a plus b. All right, so for this to happen, that means none of these events, right? None of these. Okay, if none of these events happen, okay, then my tau will be bigger than this, right? So then it will imply this event. Okay, so this will be smaller than the probability that none of the Ek happens, right? The complement of this. So let's say, so K going from 0 to n minus 1, right? So so starting from E0, so the event E0 doesn't happen, E1 doesn't happen, E2 doesn't happen, and so on, okay? Then you imply that, right, at no point, right, up to the n of a plus b time, I would not have hit my boundaries, okay? So this will be smaller than this, and we can and to compute this event, right? Note that all these events are independent, so it's just the product of them, right? And the probability of each event is nothing but 1 minus 1 over 2 of a plus b, okay? And there are n of them, right? So and they are independent, so that's why it's raised to power n. Okay? So my expectation of tau, right? Because tau is an integer value random variable, we saw before that this is nothing but we can write this as the sum of the probability of tau bigger than k. Okay. And then we can put in this bound over here. So this will be smaller than, okay, this will be. So each value of k, right, will be inside one of these intervals. Okay, each value of k will be, right, will be basically I'm dividing my time axis into all these a plus b intervals, sub-intervals. So every k will be inside one of them. So if I take the sum of all these k's, I can basically decompose it into the all these intervals, okay? And basically I'm going to just take the bigger than k, so I will just take the endpoint, right? So that this probability will be smaller than the probability of tau that is bigger than the endpoint. Okay. So a plus b, and this is true for all the k's within that interval, so there are a plus b of them, right? Times a plus b. Okay. So now, and then I'm just summing over the n's, right? N, let's say from 0 to infinity. Okay. Right, this is just an upper bound, right? So now we can use this guy over here. So this is smaller. Yeah, so we can just plug in. So a plus b sum of n right? 1 minus 1 over 2a plus b tau n. Okay, and this is a less than 1, right? So your geometric progression result tells you that this is finite, right? So this whole thing is finite. Okay. Right, so we have just proven that the expectation of tau is finite. So this implies that my tau, right, must be finite almost surely. Because if my tau is equal to infinity on a set of non-measure 0, that means my expectation will become infinite. Okay? So expectation of tau being finite implies that tau is finite almost surely. Okay. So since tau is finite almost surely, if I take the limit of Sn minimum with tau, right, as n goes to infinity, so because tau is finite almost surely, so this guy will be just equals to, as n goes to infinity, right, at some point it will be bigger than tau, right? For any given omega, tau omega is a finite value. So as n goes to infinity, at some point it will be bigger than tau. So this is just going to be equals to S of tau almost surely. All right, and then we also note that this Sn minimum of tau, right, by definition, yeah, so if n is smaller than tau, that means it hasn't hit any of the boundaries, right, either A or B, so the Sn will be somewhere in between A and minus B, right, so it will be smaller than the maximum of A and B. If n is bigger than tau, right, then it will be just equals to S tau, and then it will be the stop process, right? It will be either A or minus B. So in any case, this guy will be smaller than the max of A and B. Okay, so this is bounded. So we can now make use of the dominated convergence theorem, the DCT, right, to say that since this is bounded, right, so if we take the limit of the expectation, I can bring the limit into the expectation, right? So this implies that the expectation of Sn minimum of tau, okay, this is as n goes to infinity, right? I can bring the limit inside the expectation, and when I bring the limit into the expectation, this becomes expectation of tau, right? So this converges to expectation of tau. All right, but we know that this guy, this is a martingale, right? We saw before, and the expectation of this guy is just 0. Okay, okay, so we have just proven that these are expectation of S tau itself, right, is equal to 0. Okay, so but on the other hand, okay, we can actually compute what's this expectation. So S tau, right, is either hit A or minus A or minus B, right? So it will be equal to A if my yeah, okay. So the expectation of S tau, right? So S tau itself will be equal to A, okay, when I hit the boundary, the upper boundary first, right? So it will be equal to A with probability S tau equals to A, right? It basically just takes two values, right? So it's basically a binary variable. So it's equals to minus B, okay, when S tau equals to minus B. Okay, then I can just write 1 minus probability of S tau equals to A. So you can only take A or minus B, right? So this expectation is I suppose is obvious. Okay. So then we saw that the expectation of S tau, right? Just now we proved that it's equal to 0, right? So I can equate this to 0, so I can then solve for this probability. Okay, so this probability S tau equals to A. If you solve it, right, this is equal to 0, you rearrange the terms, this will be equals to B divided by A plus B. Okay. So that's the first objective that we have, right? We wanted to find what's the probability that I'm going to hit the upper boundary before I hit the lower boundary, right? Which is this guy, okay? Okay, but now we just proved that expectation of tau is finite, but we haven't really gotten a closed form result for expectation of tau. Okay, so to do that, we will make use of another martingale. So let mn to be equals to Sn squared minus n. Okay, so again, if you refer to last week, right, we also proved that this guy is a martingale. Okay, from last week. Okay, so because your sigma square, right? Remember last week, Sn squared minus n of sigma square, that is a martingale, right? And the sigma square equals to 1 here. So now we can, okay, we can again make use of the DCT. So first of all, we observe that this guy. So of course, this guy itself is also a martingale, right? We saw before just now. Okay, so by the martingale transform theorem, this is also a martingale. But this is also bounded, right? Because your Sn, okay, your Sn is bounded by A or minus B, right? Okay, or the absolute value is bounded by A or B, right? The maximum of A or B. Okay, so this guy is bounded by max of A square, B square. Okay, but of course we have this minus n over here. So, but this guy, right? This is the minimum between n and tau, right? So overall, it will be this will be smaller than tau, so bounded by tau, so plus tau. And we saw before from this proof that this tau here, this is the expectation is finite, okay? Right, okay, so this is a integrable function, right? So that's why we can, it's an integrable random variable, so that's why we can apply the DCT here. So the DCT will now tell me that my expectation of m tau, which is basically the limit. Okay, so from the DCT, I can get this. Okay. So this is my DCT. So now, but what is this guy? So we saw this is a martingale, right? So this is nothing but expectation of m0, right? So expectation of m0 is just s0 squared minus 0. So that's just equals to 0. Okay. So this is equals to 0. On the other hand, right, similar to what we did here, we can actually explicitly compute what's the expectation of m tau. Okay, so expectation of m tau is expectation of s tau square minus expectation of tau, right? By the definition. So m tau is s tau square minus tau, right? Okay. Yeah, right. So then we can expand out this side. So let alpha to be b over a plus b, which is the probability that my s tau equals to a. Okay. So you can expand out this expectation. So this is alpha a squared plus 1 minus alpha b squared, right? So minus expectation of tau. Okay. Right, and we saw that this is equal to 0. Okay? So I can just bring the tau over, and then I can substitute the alpha inside and do some simplification. Then you get expectation of tau is actually equals to a times b. Okay? So it's very nice, right? The result. So you can start to see the power of martingales over here. First of all, we make use of this first martingale, the simple one, the Sn, right? The martingale, to get a formula for the expectation, for the probability, okay? A formula for probability, and then we use a slightly more complicated martingale, which is the Sn squared minus n, right? To get a very nice formula for the expectation of the stopping time. So, yeah, so that's where martingales can become very useful. In a lot of problems, if you manage to find a suitable martingale, okay, then you will be able to get very nice results without much difficulty, right? Otherwise, you can see that to compute the expectation of tau is not that easy, right? Here we have to use a probability bound, but this is not even a exact value, right? So it's not an exact value. And to calculate this exactly directly is not so easy, okay? But now using the martingale, you can get the result very nicely. Any questions here? Okay, so this is okay, because this is with probability half, right? So that's why we call this a symmetric random walk. So it's symmetric random walk. You can do a more general case where now let's say Xi is biased, right? So this has probability P not equals to half, right? And then this one will be probability Q, which is just 1 minus P, okay? And again, we assume that it's IID. So in the bias case, it turns out the martingale you need to use is more complicated. It no longer, using the same procedure will not get you the results. So here we need to use a slightly more complicated martingale, which is, so I will not go into detail, you can verify, right, which is defined by this. So I take Q divided by P and raise power as n. Okay, so you can prove that this indeed is a martingale, and then from here, okay, okay, I think I'm not going to go through the details. From here, you will be able, using the similar technique as us now, you will be able to find that probability of S tau equals to A, right? The probability of hitting the upper boundary is actually given by Q over P, tau B minus 1. Right, okay. And let's see. The expectation of tau, okay, I don't have it here. Okay, you can try to see whether you can compute the expectation of tau or not. I don't, maybe that's not so easy to compute also. So, okay, so that's homework for you. Okay, you can take a look and see whether you can find the expectation of tau or not. Okay, so at least the probability of S tau equals to A, right? This using the same technique as before, but making use of this new martingale, you will be able to get this. Okay. So I don't have the expectation of tau written here. Okay, any questions here? Okay, so now we so we saw in the previous example, right? Basically, what the kind of the trick that we used was to say that, right, these are expectation of n tau, okay? And making use of the DCT, right? Because there are certain property associated with that martingale. So we are able to make use of the DCT, okay? Right. So okay, so first of all, we have this, and then we can make use of the DCT to bring the limit outside of the expectation. Okay, so we have this process, and then from our first that using the martingale transform theorem, right? We saw that this guy with the taking the minimum between n and tau, right? This is a martingale, right? So that's why we want to bring the limit outside, okay? So that we can now deal with a well-behaved martingale, so that the expectation of this is just the expectation of m0, right? Okay. So every term is equals to expectation of m0. So that therefore the limit actually doesn't do anything. It's just expectation of m0. So that was the kind of the general technique that we have been using in the example. Okay. But unfortunately, this is not always true, right? It's not always true that expectation of m tau is always equals to expectation of m0. Okay, so let's do a counter example in which this is not true. Okay. So here we have xi to be defined to be 2 power I or minus 2 power I, okay, with probability half. Okay, and these are independent. Okay. But they are not IID anymore because at each time I, right, the distribution is different. But of course, this is still a martingale we saw before. You just need independence, you don't need the IID. Okay. So this is a martingale, and we can define a stopping time. Let's say this guy equals to the first time whereby my sk is bigger than 0. Okay. So if you look at this stopping time, right, if let's say my tau equals to k, right, so this is the first time that my sk is strictly positive, okay, strictly positive. This means what? If you look at this process, it means that all my, because each time, right, if at a particular time I get xi equals to 2 power I, then the sum, everything sum up, right, will be strictly positive. So if my sk is the first time that is strictly positive, that means, right, my s tau, okay, so equals to sk. This has to be that the I equals to 1, it must be minus 2. I equals to 2, it must be minus 2 power square, and so on, right? So basically, all the xi's must be negative until the last one, right? It becomes positive. Because you can verify that, right? If as long as I have a xi that is positive 2 power I, right? Because of this geometric sum, then everything sum out will immediately become positive. Okay, so if tau, right, equals to k, that means this is the first time that is positive. That means my all the xi has to be negative all the way, right, until k minus 1, and then only at the last time step, right, at I equals to k, okay, then I get xi equals to 2 power k, and you can verify that this sum is just equals to 2. Okay, so this is true for all values of k. Okay? This is true for all values of k. So my s tau, right, is always equals to 2, almost surely. Okay, so 2, right? So that means my expectation of s tau, right, is, because s tau is always equals to 2, expectation is of course equals to 2. But if you look at the expectation of, say, s1, right? Okay, s1 is just consists of one random variable s1. Okay, so you take the expectation, this is equals to 0. Right? So this is not equal. Okay, so this example shows that, right, taking the stop process, okay, although Sn itself, right, is a martingale, taking the stop process, there's no guarantee that the expectation will be equals to the martingale expectation. Okay, so this immediately implies that, right, S tau itself is not a martingale. So our next objective is to study under what conditions, right, I can have results that look like this, whereby my stop process, okay, have the same expectation as the martingale. And that is one of the things that we will be able to give an answer to, and in fact, we will prove a result that is much more general than this. So in order to do that, we need to define this a new sigma algebra related to my stopping time. So f tau, okay, tau is a stopping time. So I'm going to look at this collection of events. Okay, so f is the whole underlying bit sigma algebra. So I'm looking at all the events, okay, whereby it satisfies this condition over here is inside f of n. Okay, and this is true for say n starting all the way, right, from 0. So what does this say? So this set consists of all events that basically depend on information, right, up to the stopping time. Okay? So when my tau, okay, right, at a certain time step n, I can determine that my process has stopped or not. And that, right, that will also determine whether, okay, that will also cover, right, the part of the omega, right, the sample points that is within this tau smaller or equals to n, okay, has to be inside my measurable sets. Okay, so I'm able to put a probability measure. I'm able to measure, right, what is the probability that, okay, my event A and my tau, my process stops, right? What's the probability of this happening? Okay. So basically, it's saying that this is the collection of all the events, right? That if I look at my information structure all the way up to my stopping time tau, okay, I'm able to determine what is the probability of this event. Okay. Okay, so yeah, so it turns out that this is a sigma algebra. Okay, so we can prove it. Right, you just have to check that it satisfies the definition of a sigma algebra. Okay. Right, okay, I don't need to go through this. So let's look at some simple properties, right? So what's so nice about this sigma algebra f tau? So from the notation, it seems to suggest that is of course it's closely related to the stopping time, and okay, and we can show that this stopping time, right, itself is measurable with respect to this sigma algebra. So tau is, okay, remember we use this notation, right? This is a random variable. When we use this notation, we just mean that it's measurable. So this just means that tau is f tau measurable. Okay, so how to prove this, right? So what we need to do is to prove that tau is f tau is some sigma algebra measurable. We need to prove that this tau, right, is this event, right? All these events is inside the sigma algebra. Okay, for all k, right? Because your tau, right, is an integer value random variable. So we just have to prove that all these sets, right, all these events are inside that sigma algebra of interest. Okay. Okay. So in order to prove that this is inside here, I just need to verify that this is true, right? So my A is now this event. So what I'm wanting to do is to prove that this intersect with tau smaller or equals to k, right, is inside f of n, right, for all values of n. Right? So for any fixed value of k, any fixed integer k, I want to prove that this guy is true for all values of n. Okay. So if you look at this is nothing but what is equivalent to the event where tau has to be both smaller than n and smaller than k, right? So smaller than n minimum k. K. Okay, and by definition, right, tau is a stopping time, so we know that this guy is inside f of n, minimum k. Okay. Okay, but since we are dealing with a filtration, right, this is nothing. Will be inside f of n, right? So we are done. So this is true for all values of n. Okay, so we have proven that right? For any fixed k, this is true for all values of n, and basically that means that this tau smaller or equals to k has to be inside f of tau, right? And it means that tau is f tau measurable. So any questions here? All right, so another result that we have is, if let's say I give you a martingale, mm, this is martingale, this is adapted, so adapted to fm. Right, remember this adapted means what? The mm is fm measurable for every n, okay? For every value of n, mm is fm measurable. So then, right, then we have, okay, so that also assume that tau is finite, almost surely, so that we can define m tau. Okay? So then this, if mn is adapted to fn, then it turns out that m tau is f tau measurable, so it's also adapted to f tau. Okay? So m tau itself is a random variable, right? This is f tau measurable. So the notation seems to make it obvious, right? That's why we choose this notation f tau instead of calling it, give it a different symbol. And the advantage of this notation is that it makes these kind of results look obvious, but of course, it's not trivial, right? Because this f tau is defined in a very specific way. So in order to prove this is true, we need to check that this condition holds. Right? So how to prove that this is m tau, right, is f tau measurable? That means I want to show that, right, all these events, m tau inside some Borel set, okay, for all any b, right, for all b that is Borel, okay, I want to show that this guy is inside f tau, right? So which means that I want to show that this, according to this definition, I want to show that tau smaller than n intersect with this guy, right, has to be inside fn. Okay, so I want to show that this is inside fn. So I can expand this tau smaller or equals to n as a union. So this is union of k smaller or equals to n, right? Tau equals to k. Right? Now intersect with m tau inside b, right? So m tau inside b. But now because I'm intersecting with the event tau equals to k, so I can replace the tau with k. Okay, if you look at whatever is inside here, right? So tau equals to k, this event is inside fk, right? And mk inside this Borel set. So we assume that mk is inside, is measurable, is fk measurable, right? So this event is also inside fk. So that means the intersection of these two events is inside fk because it's a sigma algebra. And of course, my k, right? My k is smaller or equals to n, and this is a filtration, so this is inside fn. Okay? So that means the whole thing, right? So all the terms inside this union is inside fn. So the union, right, will be inside fn. Okay, so then we get the result, right? So then we get this visually appealing result, okay? But of course, the proof is itself, right? I mean, you cannot immediately say that this is true, right? Okay, any questions out of here? Okay, so now if I give you two different stopping times, tau and nu, right? Both of these are stopping times. Okay, two different stopping times. So it turns out that all these events, tau less than nu, tau equals to nu, tau bigger than nu, all of these are inside f tau, as well as inside f nu. Okay, so all these events belong to both these sigma algebras. So you can write the inside the intersection of these two sigma algebras. So all these events will be inside both of these sigma algebras. Okay, let's prove the first one, right? Then the rest I think you can handle yourself. So to prove that this guy, let's say I want to prove that this guy is inside F tau, right? That means according to this definition, I need to show that tau smaller than n intersect with this event. Right? I want to show that this is inside Fn, right? Okay, so we will use the same technique as above here, right? Decompose this into a union. So union of k smaller than n, tau equals to k, and then intersect with. So now my tau I can replace it to be k, right? So is this will be nu bigger than k. Okay. So again, this is inside fk, right? This is inside fk, and because nu is itself a stopping time, right? So this event is inside fk as well, okay, by definition. All right, so using the same argument as above, right? This will be inside fn. And similarly, you can get the using the result for the others. Okay. Okay, so now if I give you an event inside f nu, okay, then this event intersect with tau bigger than nu, okay, as well as this event intersect with say, okay, strictly bigger than nu also. Okay, so either of these events, both of them will be inside f tau. Right, so what does it say? It says that, right, so an event A inside this F nu is basically all those events, right, that you can that depend on information, okay, up to the stopping time nu, right? So when your stopping time nu reaches a certain criteria, right, your process stops, then you are able to measure, right, what's the probability of that event, okay, condition, I mean on the set that nu is smaller than n, okay, or nu equals to some value n, okay. So this event basically consists of information, right, that depends on your stopping time nu. You have your stopping time nu has the full information on this event. And what this result is saying is that if I give you another stopping time, right, and this stopping time is okay. So first of all, okay. So if I give you another stopping time, and this stopping time, let's say is going to be, you are going to stop the process only after nu, right? You define another stopping time in such a way that, okay, maybe I should use another analogy, right? Think of this stopping time as, for example, you are buying stocks, right? You are buying stocks in the stock market, and this stopping time is basically, you can think of it as a strategy, right? Telling you under what criteria you are going to sell your stock, okay? So you want to find a stopping time in such a way that, right, you define a set of criteria at which you know, if the conditions are true, then you want to sell your stock, right? Then tau is another strategy, right? It's a different strategy from your original one nu. Okay. So this thing over here is saying that, right, this new strategy tau is going to be stopped later than your original strategy nu. Okay. So if you do that, right, then this event over here, right, this event here, your event A will actually depend on the information. It turns out that, right, if I have a strategy that is always stopped after the nu, okay, then my event A, right, will also be inside this F tau. Okay? So this new strategy, in some sense, right, if I can define this new strategy tau in such a way that is always stop after the new, right? So think of this, right? If that's true, right, then this is just the whole omega, right? Then it's just A itself. Then this A is also inside F tau, right? So the A will depend on information only up to the time, the new strategy tau. Yeah? Okay, so well, okay, we will make use of, so in the next theorem that we are going to discuss, we will make use of this fact. It may not seem that important as of now, okay, but yeah, this is just one interpretation, right? So it's basically, yeah, in some sense, it's saying that, right, whatever new strategy you define, you cannot extract more information, okay, out of it if you are working with a martingale, okay. So let's try to prove this. Okay, let's try to prove this. So let's see. Right, so I want to prove that this event is in F tau. That means I want to prove that this tau smaller or equals to n, right, intersect with this event over here. I want to prove that this is inside Fn, right, for all values of n. So actually, again, all these proofs are actually quite simple. It's always using the same technique, right? So break this into a union of sets. So now my tau equals to k. Okay? Intercept of A and tau equals to k, right? So I can replace tau with k. So my nu will be smaller than k. Right? Okay, so now we can see that by definition, right? A is inside F nu. So this guy, by definition, right, is inside Fk, right? Then of course this is inside Fk. So the whole thing is inside Fn. Okay? Okay, so the proof is straightforward. Okay, and then we have one more. So if tau is always smaller than nu, right? So your new strategy, let's say, is always stop before the old strategy nu. And if this is true for all, say, omega, let's say, then f tau would be inside f nu. I guess this is obvious, right, from the definition. Okay, so if tau is always smaller than nu, right? So tau smaller than or nu smaller than n will imply that the tau is smaller than n as well. So this is obvious. Okay, so now we come to the important theorem. So this is Doo's optional stopping theorem. Okay, so it says that if I'm working with a martingale, MM in this is a martingale. Okay, and I give you two stopping times, right? So again, think of this as the two strategies that you have, right, for selling your stock. Okay, so tau and nu are two stopping times, okay, or two strategies. Moreover, your stop process, say at tau, okay, this is finite, okay, so this is integrable. And also you need to satisfy another condition that the limit of this mn, okay, this is going to 0. So as n goes to infinity, right, your expectation, okay, your expectation on the set where your tau becomes very large, right? This is going to 0. So your tail gains are very small. It's going to 0. Okay. Then the theorem says that for all events A inside F nu, right? So again, right, this F new is the sigma algebra associated with your stopping time new, right? So I'm looking at an event A that is inside F new, right? So basically the at the stopping time, I'm able to determine the event A, right? I have all the information of A up to the stopping time new, okay? So if I do an event like this and I look at the M of tau, right, on the restricted to this event whereby, okay, let me write it out first. And so this expectation is going to be the expectation when I take N of mu on the same event. Okay, so it may not look so easy to interpret. So let's look at one simple example first, right? So for example, let's say I take my A to be omega, right? The whole sample space, and by mu to be 0, that's a constant, right? So a constant by definition itself is a stopping time. So then what do we have, right? So on this side here, so tau is always bigger than 0, okay? So you are going to get expectation of m tau, right? Expectation of m tau. And then on this side over here, right, you are going to get m0, right? So expectation of m0, which is, remember, this is what we want, right? We wanted to ask under what condition, right? If I give you a martingale and a stopping time, okay, when does the expectation of m tau equals to expectation of m0, the martingale expectation? Okay, so this optional stopping theorem basically recovers, basically says that, right, these are the conditions, sufficient conditions for this to happen. But of course, this theorem is much more general than that. So this is one example. So another example is, again, the tau and mu, right? These are two strategies, right? So there are two different, say, your stock selling strategy, okay? So what does it say? It says that, right, so this event A, right, is inside F new. So meaning that my strategy new or my stopping time new, right, he has basically full information about this event A, right? So when my stopping time new, my process stops, right, I am able to compute what's the probability of A, right? So I have full information about A. Okay, so even in that case, right, if I give you another strategy, another competing strategy tau, you can see that no matter what strategy I'm going to construct, the amount, okay, think of your mn, right? This is your stock price or your wealth, right? The amount of gain that you are going to get by selling your particular stock, right? So no matter which strategy I give you, even on the event A, right, where the original strategy, the new has the full information, you can see that, right, the amount of wealth, right, that you get, expectation of m tau on the same event is going to be the same as the old strategy, right, the original strategy. So it says that, right, no matter what strategies I'm using, okay, if my process is a martingale, right? For example, we talk about the efficient market hypothesis, your stock price under the efficient market hypothesis is a martingale. Then no matter what strategy I use, right? Even if I have an advantage, right? I observing events on those events that the first strategy knew has the full information, but your tau need not have the full information. We are still, in terms of the expected wealth, we are actually still going to be the same. Okay, so no matter what you do, right? Okay, so this theorem basically says that there's really no winning strategy, right, in an efficient market. No matter what you do, okay, no matter how clever you are, whatever strategy you come up with, right, you cannot do better than any others. Okay, so before we prove this theorem, let's go back to just now that counter example, right? To show that why, right? Why it's not true, because so it turns out it doesn't it basically validates this condition over here, right? So remember this counter example that we have, right? So the expectation of S tau is equals to 2, so it's not equals to 0. It's because right, it doesn't satisfy this condition, because why your in this case, right? In this case, okay, for S tau, remember your S tau is basically the tau is the first time when it becomes positive. Okay, so in order for it to become positive, right, it has to obey this sequence. Right, it's all negative, all the xi's are negative until the last one becomes positive. So the probability, okay, of tau equals to n is always equals to 1 over 2 power n, right? Okay, so because it has only one path, right, one sequence, and so this guy is 1 over 2 power n. Okay, so we can now compute this Sn tau bigger or equals to n. Basically, we are trying to verify, see this condition over here. So if you go and compute this guy, this will be what? Okay, so you can break it out into tau equals to n and tau bigger than n. So when tau equals to n, right, you will get exactly as tau is equals to 2. So probability of tau equals to n. Okay, and then on the set where tau is bigger or equals to n plus 1, right? So Sn, that means all the terms, right? All the xi's inside this Sn will be all the negative, right? But of course, we take the absolute value, that means yeah, basically summing out all the 2 power i's, right? So this will turn out to be 2 power n plus 1 minus 2 probability of tau bigger or equals to n plus 1, right? Okay, and then you can substitute this inside. You can show that this is actually equals to 2, okay? So no matter what's the value of n, okay, as n goes to infinity, is going to stay at constant 2, right? So it validates this sufficient condition. So in that sense, this condition is actually essential, right? So the example tells you that without this condition, you don't have any hope of getting this this result over here. Okay, let's try prove this theorem. Okay, so we start with A, right, inside F nu. So for convenience, I'm going to define An to be A intercept of this nu equals to n, right? So this is just for convenience. So by definition, right, we know that this guy is inside Fn. Okay. Right, so our first, okay, so let's look at this. So expectation of Mn An intercept of tau bigger than n. All right, okay. So I basically want to show that this guy, I can replace this n with tau. Okay, so let's work it out. So this guy over here, this is equals to, so I break it up into 2 parts. An, so tau equals to n, and then another part where tau is strictly bigger than n. Right? Okay. So if you look at this guy over here, right? So tau equals to n, that means I can replace my n with the tau, right? So, okay, so this part is the same as m tau, right? Okay. Okay, now I need to, so I want to find a way to replace the n with the tau. So let's look at this part. So recall that this mm, right? This is a martingale. So this guy will be equals to what? Expectation of m plus 1 condition on fn, right? So that's your definition, your property of your martingale. Okay, so let's plug that in, and we are going to get expectation of n plus 1, right? And notice that, and this is condition on fn, right? And notice that this guy over here, right? This is measurable with respect to fn, right? Because an is in fn, this event tau bigger than n is also in fn. Okay, so this indicator is measurable with respect to fn, so I can bring it inside. So let's bring this guy inside. Given fn. Okay, and remember we also have a result where we have this kind of nested expectations. So the one with the smaller sigma algebra always wins, right? So the expectation of this guy is just the one without the conditioning. Okay. Or you can also get the same result from the basic definition of conditional expectation, right? So by the basic result, right? This is by definition is equal to just the expectation of this. Okay. Right, strictly bigger than n is the same as bigger or equals to n plus 1, right? Okay. Because tau is an integer value random variable. Okay, so down here we can see that what have we done? We have basically shown that, right? From the n, we becomes the n plus 1. So, but the an stays the same, right? So now if I do the same thing all over again, I will be able to show that this is equals to expectation of n plus 2, right? With the indicator an intersect with tau bigger or equals to n plus 2, and so on, right? So by induction, okay, so using induction, you can, so this is equals to expectation of m, okay, an intersect of tau bigger or equals to m, right? For all values of m, say bigger or equals to n, okay? So this is true, right? Sorry, did I make a mistake? Yeah. No, sorry, this is not true. So the induction, okay, so what we have shown here, right? This is bigger or equals to n plus 1. What we have shown here is from here to this guy plus this guy, so sorry. Okay, so I need, let me write it out properly. Plus bigger or equals n plus 1. Okay, so you need to be careful. The form has to be correct, right? Bigger or equals n plus 1, right? Okay, so if you do at this guy with this guy, right? Okay, what we have shown here is that each time, right? So by induction, right? If I want to change this to m, right? Each time I do the same process, okay? I do the same process, I'm going to get one more term outside here, right? I will get one more term, and then this guy will be equals to this, but with the n plus 1, and then plus the n plus 2, and so on, right? Okay, so each time I do the induction, I'll have one additional first term at the front, okay? So by induction, I will get m tau en. Okay, so now my n, right? This is tau equals to n, and then by doing one more step, I will get another term where tau equals to n plus 1, and then tau equals to n plus 2, and so on, right? So I can combine all of them together to give me this, right? Tau smaller than m, okay? Plus an tau bigger or equals to m. Okay, and this is true for all m, right? Is everybody okay? Okay, so let's look at this guy over here. Yeah, so you recall that we have this condition, right? The expectation of the m tau, right, is integrable. So we'll make use of it here. So this this over here, right, is dominated by the m tau. Okay, so and the expectation is integrable. So I can apply the dct. So using dct, okay, and let m go to infinity. Okay, as m goes to infinity, the dct tells me what this term is going to approach to bring the limit inside, right? It's going to approach to expectation of m tau an intersect with, right? So the m goes to infinity. This event will be just tau bigger or equals to n, right? Okay. So if I do the same on this side, right, as m goes to infinity, I want to do right. Okay, so this guy over here, right? So if I take the absolute value, this will be smaller than mm. Okay, and I can throw away the an, right? Okay, so it will be smaller, right? If I throw away the an, this will be smaller, bigger than m. Okay, so this thing, the absolute value is bounded by this, and then we saw, right? This is another condition that we had, right? So the third condition, as n goes to infinity, this goes to 0. So as m goes to infinity, this side is going to 0. Which means that this whole thing will convert to 0. Okay, so what have we proven? We have proven that, right, if I take the m go to infinity in this expression, this whole thing, right, is going to converge to this guy. Okay, so which means that what we have shown here is that this over here is equals to this over here, right? Okay, so basically I have just replaced the n with the tau. Okay, so what's the use of this? So then finally we can make use of this result, right? So we want to prove that this expectation of m tau of a intersect with this guy, I want to prove that this is the same as expectation with the m nu instead of the m tau, right? So this will be equals to okay, I'm going to rate according to the value of nu. So sum of a n bigger or equals to, we start at, okay, the starting point, let's say, is 0. So m tau, so nu equals to n, right? And now this is on the event nu equals to n, so I can replace my nu with n. Okay. Right, this guy over here, this is by, just how we just define an to be this guy, right? So this is just a shorthand notation. So this is just your an, right? So what we have proven just now is that this over here, right? This expectation over here is equals to this. So I can just replace it with expectation of mn. Okay? And this is just my an. Right? Okay, I rather write it out a because I want to go backwards. Okay. right? Okay. So you can see, right? So this is restricted to new equals to n. That means I can replace all my n with new, right? So this is the same as, and then when I sum it out, this is basically breaking out, right? The over in breaking out over the events new equals to each value of n, right? And then if I sum it out, that means I can just replace the n with the new. So n new, right? A inters. Okay, and this sum will so go away, and then this intersect with tau bigger or equals to new. Right? Okay, so it's the same as this guy. It's just basically from here to here. I'm just reversing, right, back to here. But now it's with the new. Okay, and this is what we want to prove, right? Okay. Um, okay, so just to point out a few things. Just now, the the stopping, the optional stopping theorem we saw, right? This is one of the simple cases. There are other simple cases also whereby, let's say, now if my tau, right, is always bounded, this is a bounded stopping time. Okay? It's a bounded stopping time for some b, right? Is a bounded stopping time. Then you can verify that, right, all these conditions will hold, right? Okay, so this will definitely hold, right? Because your martingale, we have assumed that all the mm's are integrable. Okay, and then this will also hold, right? Because tau is bounded. Okay, so as n goes to infinity, this will go to zero. Okay, so yeah, so if you have a bounded stopping time, then your optional stopping theorem will hold immediately. Another case is where, let's say, your martingale itself is bounded. Okay, so this is, say, is bounded by some k, right? Then yeah, so this will definitely hold, right? Because it's bounded by k. Now we just need to check this guy. So your expectation of mn as, okay, right? Mn is bounded by k, so this is smaller than k, or probability of tau bigger or equals to n. Okay, so as okay, so we had assumed that the stopping times are finite almost surely, right? So as n goes to infinity, this will go to zero, right? So this will go to zero. Okay, so the third condition will hold almost trivially. Okay, so these two cases, your optional stopping time will you can apply them immediately. There's also other results whereby you actually don't need these loops optional stopping time, but you can still get similar result whereby the expectation of m tau equals to expectation of m0. So we have another another result that doesn't need this, but you need a stronger condition. So in this case, we have the so-called bounded increments. So mn minus n minus 1. Okay, so the difference between subsequent variables inside your martingale process, this is bounded. Okay, so bounded by some constant, almost surely. And moreover, if the expectation of tau is finite, okay, then this implies that the expectation of m tau is equal to expectation of m0. So let's give a quick proof of this. Right, so let's look at this guy over here. So this is we can write it as a telescoping sum, right? Okay, so up to n minimum of n and tau, right? So these two are exactly equal, right? Okay. So now, because of this bounded condition, right, the bounded increment condition, I bring in the absolute value. So each of these term will be less than k, and then there's is at most tau of them, right? This is the minimum between n and tau. So at most tau of them. So the whole thing will be smaller than k times tau. Okay. So, and because we assume that this is integrable, so now we can apply your DCT. Okay? So DCT will imply that this expectation of m tau, right, will be just taking the limit. You can take the limit outside of this guy. Okay. And we saw before that this is a martingale, right? This is a stopping time. We have proven that this is a martingale. So the whole thing is just expectation of m0. Right? Okay. So if you have a stronger condition, then you can get this kind of result very easily, okay, without that optional stopping theorem. And moreover, actually, in this case, okay, in this case, you can also get stronger results that says that, right, if now I have an which is predictable, okay, so if this is predictable and bounded, then remember your martingale transform, right? So your mn tutor, your martingale transform will also, we know that this is a martingale, but how about the martingale transform of evaluated at tau, right? So it turns out that you also have this property, okay, which is the m0. Okay. So I'll leave the proof to you guys over here. This is quite simple. You just have to follow the definition of the martingale transform. Okay, any questions here? Okay, I think for this result to hold, you do need this stronger condition. You should be able to find examples whereby just the conditions in the loop optional stopping theorem would not give you the martingale transform is also have this property. Right? So you do need this kind of stronger condition. Okay, so finally we will end by looking at quite a famous problem. So this is called the abracadabra problem. Abracadabra problem. Right, so what is this saying? So basically it's saying that okay, if I give a monkey, right, a typewriter, and the monkey is typing a letter at random, right? Assuming this typewriter has only 26 of this kind of English letters. So this monkey types a letter at random at each time, okay, uniformly and independently, okay. And we want to know what is the expected time for the monkey to first produce this sequence, abracadabra, right? So probably you have heard of different versions of this problem, right? Where let's say, right, we can prove that the probability that a monkey can type out the whole words of Shakespeare, right, in a finite amount of time is equals to 1. Right? Okay, so it's the same kind of problem. And usually people will try to solve this problem using the theory of Markov chains. You can set this up as a Markov chain, and then you can analyze the yeah, you can also define a stopping time in your Markov chain, and then you can analyze what is the expected stopping time or hitting time of this state, okay, inside your Markov chain. But now let's look at how we can solve this problem almost trivially, almost immediately using using your martingale theory. Okay, so let T, right, to be the stopping time that we are looking for, right? So T is the first time that your monkey types out this sequence. Okay, so basically we are trying to look for expectation of T. So in particular, this is a stopping time. Okay, T is a stopping time. Yeah, you can prove that these expectation of T is finite. Okay? So basically using the same argument as just now, when we prove that the stopping time is finite in the random walk, right? So you can set out something like this, you can prove that it's finite. Okay, so this part I'm not going to go through. So finite means that my T, right, is finite almost surely. Okay? So now let's try to design a martingale, right, to solve this problem, right, and making use of your optional stopping theorem. Okay, so how to do this? So we assume, right, at each time, okay, at each time j, okay, at each time j, I have a new gambler, okay, a new gambler, okay, a new gambler arrives, and this gambler is going to bet $1 that the jth letter is equals to A. So he's always going to bet, okay, the first letter inside this sequence. So he's going to bet, right, at this time, J before the monkey types the letter, he's going to bet that, right, he's going to type the letter A, okay. So if he loses, so there are two situations, right? If he loses, that means the monkey types another letter, not A, then he will just leave, right? Okay. If he wins, right? If indeed the monkey types the letter A, okay, so I need to write it down, bets on A, bets $1 on A. Okay. If he wins, then he will receive $26. After he receives $26, he's a compulsive gambler, okay? So he's going to bet everything, okay, in the J plus 1 time, okay? So he's going to bet all 26, right? All his wealth, right? Bet all on the J plus 1 letter, right? Is B, right? Basically following this sequence. Okay, so each time, if he at any point in time, if he loses, he will just leave, right? So he will lose all the money. If he wins, right, he will now take everything and bet it on the next letter. Okay. If he wins again, right, he will bet everything on the next letter, right, and so on. Okay. But okay, so this is the first gambler. He comes in, he will do the betting. If at some point, right, he loses, right, he will just leave. But at each point in time, so in the next time equals to 2, there's a second gambler who will come in and do the same thing all over again. So the second gambler will bet A here, B here, R here, and so on, right? Okay, so for example, let's say the first gambler, he comes in, he bets A, he wins, he will stay, right? He will bet B. So at time 2, there's a second gambler. So there are actually 2 gamblers, right? 2 gamblers at time 2. Okay, and the second gambler will bet A while the first gambler will bet B. Okay, and then maybe at the third time, okay. Sorry. So at the second time, if let's say the monkey types the letter C, right? That means both gamblers will lose, right? Then both of them will leave, right? Then at the third time slot, the third gambler will come in, right? So now at the third time slot, there will only be 1 gambler, and so on. Okay. So is that clear? Okay, so I can now let Mn of J, superscript J, this is the wealth, okay, wealth of gambler J, okay, at time N. Right, so this wealth, right, if the gambler leaves, that means this wealth will be zero, right? I will set it to be zero. If he wins, then it will keep increasing. Okay, so the maximum possible value is basically he bets the whole sequence, he's correct. So the maximum possible value will be what? Will be each time, every time he wins, right? So it's bounded by 26 to the power n minus j plus 1. Right? Okay. Of course, this is true for almost surely, so the expectation is also true. Right? Okay. Okay, so now let's try to compute the conditional expectation. So condition on all the observations up to time n minus 1. So this Fn is basically the sigma algebra of the random variables, which is the letters that's typed by the monkey, right, up to time n minus 1. Okay. Right, so basically, this sigma algebra is generated by the random letters that is typed by the monkey up to time n minus 1. Okay? So basically, condition on observations of the letters, right, up to time n minus 1. So what is this L? Right, so it can be equal to 0. Right, if that means he bets the wrong thing, he loses. Right, this gambler J loses. So this will be equal to 0. And it's going to be equal to 0 also if that means if the gambler loses before time n, right? So if this gambler, right, J loses before this time n, okay, so that means it has already left, right? So you by definition will set equals to 0. So this will be equals to mj of n minus 1. Okay. Okay, but at the how about if he doesn't lose before time n, right? So he's still in the game. He's still in the game at time n. So then there's a probability that he can lose. There's a probability that he will win, right? So 1 over 26 probability he will win, right? Okay, but for him to win, that means if he hasn't lost before time n, that means he has won all the time, right? He has won starting from time j all the way he has won. Otherwise, if at any point, right, he loses, he will have already gone out, right? He will be 0. Okay. If he hasn't lost before time n, that means he has won all the way. Okay, so that means he will have already accumulated the wealth, and then including the one at time n, right? It will be multiplied. Okay, so you have 26 to the power n minus j plus 1. Okay, and then of course with 25 over 26 probability, right, as long as the letter is not correct, you will lose, right? So you will have become the wealth will be 0. Okay? So this will be equals to what? 26 to the power n minus j. And indeed, right, this is the wealth because he hasn't lost, right, before time n. So he will accumulate the wealth all the way up to time n minus 1, right, which is this wealth, which is equals to n minus 1. Okay. Right. So because he hasn't lost before time n, right, so the wealth up to n minus 1 is exactly equals to this. Okay. So we can see, so what have we proven, right? We have proven that this guy, no matter what situation, right, is always equals to this, right? So it means that this mnj, right, this is a martingale. So mnj, right, is a martingale. Okay, so now I can add the wealth or the payoff of all the gamblers together. at time n. Okay, so I can let Sn to be the sum of all these mnj's, right? So your j is from 1 to n, right? So at each time you have a new gambler coming. So I'm going to add up the payoff of all the gamblers up to time n. Okay? Because the gambler at the beginning it takes in $1, so I'm just counting the payoff. So -1. Okay. So this is basically the gain, right? The total gain that you have, or the total payoff, okay, of all the gamblers at time n. So yeah, so since each of them is a martingale, right? You can prove that this sum itself, right? This mn is also a martingale. Okay. So this one is easy to prove, so we can show that this is actually a martingale also. Right? Because each of the term itself is a martingale, so you can easily show that this is a martingale. Right, so since this is a martingale, and moreover, right, is a bounded martingale. Okay, so the bound is what Sn is. So when will this guy not be equal to 0, right? Is when this gambler, right, up to time n, he has won all the way, right? He has won all the way, then it will be positive, right? Otherwise, it will be 0. Okay, and of course, then the total payoff will become -1 lah. So in any case, right, this will be smaller than. So when will he win all the way? So if you happen to have a gambler, right, that bets A at the first time, right, bets B at the second time, R at the third time, and so on, right? So if you count, there are basically 11, right? 11 letters over here. So this at most is bounded by 26 power 11 plus, let's say you have another gambler that comes in at this time, right? And he bets the same sequence. Right? Remember, your gambler is always betting abracadabra, right? He's always betting the same sequence, A, B, R, A. Okay, so if I have a gambler that comes in at this time and I bet A, B, R, A, right? Then the maximum wealth, right, that I can get is this A, B, R, A, right? Is there are 1, 2, 3, 4, right? 26 power 4 here. So that's your payoff. And then of course the last one that comes in, right? You will get a payoff of 26. Okay, so this whole thing is bounded, right? So in any case, this is just to prove that this whole thing is bounded. Okay? Yeah, right. So we saw that since it's bounded, just now the optional stopping theorem. Then so using the optional stopping theorem this is a bounded martingale, so I can apply the conditions of this optional stopping theorem will apply immediately, right? So this will imply that expectation of st, okay, this is my stopping time, is equals to expectation of x0, and x0 is 0, right? I start off with 0 payoff, and expectation of st, okay, this will be what? So we can compute this. So at the stopping time, right? That means the first time the monkey types out this whole sequence, right? This is the stopping time. The first time types out all sequence. So it will be exactly correspond to this case, right? So if my monkey the first time types out this whole sequence, that means I will have one gambler that will get exactly 26 power 11, right? And then I have another gambler that will get exactly 26 to the power 4 plus basically the upper bound plus 20 plus 26. Okay? And then of course I need to the payoff, right? -1 minus t up to time t. Okay, so xt is equals to this minus t, and then the expectation. Okay, so and now this is equals to 0, right? So that means my expectation of t is just this guy. Okay. So expectation of t is just 26 power 11 plus 26 power 4 plus 26. Okay. So that's how we get this thing over here, right? So that's how we compute the expectation. Okay, as I go along, I think I may make a mistake here. This guy, this is not the true upper bound because of the -1. Okay, so probably we cannot use this bound here, but rather we should use something like xn minus 1. Okay. Right. So if I look at this guy, this will be bounded, right? This will be bounded by 26 power 11, right? If the basically is just the difference of one gambler, right? So the maximum value that one gambler can get, okay, so -1, right? Oh, because it's already minus, okay, so the -1 cancels out. The one gambler, the maximum value wealth that the one gambler can accumulate is bounded, okay? So then we just have to make use of the other result, right, where it has a bounded increment. So we will also get this. Okay, so not sure if it's still true or not. Okay, so this one you can check. But this one is easy to see. Okay, so as you have these bounded increments, then you can get this result immediately also. Okay, any questions here? All right, okay. Questions? So yeah, so you can see if I can design a martingale nicely, right? You can design something that has this martingale property, then to compute this kind of expectation of stopping times becomes very simple. Okay, if nothing, then we stop here today, and yeah, then next week we will start on the topic of sub-martingales and then go on to the conversions of martingales. All right, okay, thank you.
Thanks.